Good morning, everybody. Today I will discuss the concept of stability analysis. So, a system is said to be stable if the response is bounded output finite within application of bounded input, whereas if the output approaches towards an infinite value, then the said to be unstable. So in this linear system, a linear time invariant system to be stable, so it is some criteria. First criteria, when a system is excited by a bounded input and output is bounded. So this type of stable system is called BIBO stable. Okay. Here some example I will show you. Some bounded input, that time is increases t, this is the time and this is the RT, the reference input signal. So this is the actually when time t equals to 0. So this is actually, you can consider this is the 0, and some after the some time it also, this is actually value will be 0. So this is actually bounded input. Okay, when this type of signal actually apply to the system and you can get the response Ct is tends to 0. So this type of system is called BIBO system, bounded input and bounded output system. Now without input excitation, the output tends towards 0, which is known as asymptotic stable. Asymptotic stable will be considered also. This is the bounded input and bounded output system. Some unbounded system means when system input is bounded but the output not bounded, means it is when time will be increases. So at that time you can see the time will be increases, t tends to infinity, so it will be increases with respect to time. So this type of system is called bounded input, the output is unbounded. Okay. Now stability of control system, there are several meaning of stability. In general, there are two kinds of stability definition in control system study: absolute stability and another one is the relative stability. What is the absolute stability? The term of absolute stability is used to relation to qualitative analysis of stability. That means we can consider some system, that system parameter you can simplify and analyze. After that you can consider system is stable or not. I will discuss later the system stable, unstable and marginal stable, that also parameter of the stability. Now relative stability term relative stability used in relation to comparative analysis of stability. If the system is stable, then we determine how system, okay, this is actually mistake, how system it is how system stable, that is we measure the degree of stability. The parameter of this relative stability, the gain margin and phase margin, that frequency domain analysis parameter. Okay. Now stability with respect to pole location in the S plane, that means we are handling the absolute stability of the pole location of the system, you can see if all the pole of the system left half of the S plane, left half plane, so the system said to be stable. If any of the pole lie of the right half or right half of the plane, the system said to be unstable. And if pole lie in the on the imaginary axis, so that time system to be marginal stable. So in this figure I will show you, this is actually a real part, real, and this is the imaginary. Okay, so in the S plane, when you can calculate the pole and 0 from the transfer function, after you can locate of this pole, only pole of the system, after that your decision, or we can decide the system stable or unstable or marginal stable. So you can see this is actually portion, this is the left half portion. If any pole exists in this position, so stable, this is, you can consider this is the stable region, or system will be stable system. So this is also, and this is the portion actually we are marking red color. So this is actually portion of the right half of the S plane. So this is the unstable region, means if any pole exists of the right half of the S plane, so system will be unstable. Now some pole of the system, suppose some transfer function is given, some transfer function is given, means you can consider some numerator and denominator, you can calculate denominator value. Okay, after that denominator, it will be find the pole. After you can plot, some pole will be exist in your left side. Okay, some position, but some one pole of the right half of the S plane, one pole. So that time you can say system will be unstable. Means thousands of pole or millions of pole left half, but only one pole exists of the right half, so system to be stable. Okay, I will give you the example, some example that actually helpful for understanding. Pole okay, pole on negative half of S plane. That means we can consider some poles S equals to minus A. Okay, the impulse response, what will be the transfer function? So transfer function will be, suppose this is the CS CS by RS, if you are right, so that will be, we can consider gain K, so S plus A, that will be our transfer function. Okay, so what will be the CT? CT will be written as Laplace transform of, suppose this is actually GS, if you are right, so Laplace transform of GS Laplace transform of K by S plus A. So you can get, this is the K by e to the power minus AT. Okay, so if you are plot a system pole location imaginary, so here will be your pole minus A. Okay, now this is the real, means this is the minus real. Okay, So here this is the minus a is exist. Now Ct will be k into e to the power minus at. So if you are at t tends to infinity, so impulse response of Ct approaches to 0. So what will be the response if this is the Ct and this is the time t? So you can see when t equals to 0, so you can get some k value in this position. This is actually position, you can get this is the k. After that it will be time will be increases, so it will be decreases nature. Okay, so this will be the impulse response of the Ct. So pole negative half of S plane. So when t tends to infinity, response will be goes to the 0. So that time we can say system is stable. Okay. Now another consideration, pole on positive half of S plane. So here also consider S equals to A. So before I'll consider S equals to minus A, that actually negative half, this is the positive half. So what will be the location of pole? So location of pole, this is the real, this is the imaginary, and this is the minus imaginary, and this is the minus real. So pole will be, this is the A. Okay, so what will be the your system impulse response? Impulse response Ct equals to Laplace inverse k by S minus A. Your transfer function will be, suppose a Cs by Rs, that will be k by S minus A. Okay, so k is the gain, nothing but a constant value. So you can consider also 1 by S minus 1. So when you can calculate Laplace inverse, so that value will be k into e to the power at. Okay, so impulse response when you can calculate, so we can vary t equals to 0 to t equals to infinity, t tends to infinity. So what will be the response? So when you can plot the Ct output, so that will be time, and this is the Ct is your output, time varying. So you can consider when t equals to 0, so this value will be 0. Sorry. Okay, now you can get some k value. So this is actually k. After t tends to infinity, so you can put this value t in place of t, so it also you can get the infinity. So the response will be this type of nature. Okay, so it is doesn't come to the tends to 0 position. It is always t will be infinity, so your response also some infinite value. Okay, so that time your decision will be system is unstable. Okay, so in this way you can judge each of in every parameter of the system. That parameter actually depends on the pole, and you can judge the system stable or unstable system. Okay, now here I show you some system response. Some we know the some real negative real pole, some imaginary axis. Symmetric pole actually exists in imaginary axis, but all that value actually negative, means you can say this is the -2 plus 3j, and this is the -2 minus 3j. So this type of pole response will be give, this is actually it is coming from this city output, coming from the some finite position, and it will be time will be in infinity, or time will be increases, so response tends to 0. So already I will show you this type of graph. Now also already show you the negative positive half if pole is exist. So this type of graph you can get. Now this is actually imaginary position, real symmetric position, the two positive pole, means you can say this is the 2 plus 3j and this is the 2 minus 3j. So you can calculate the transfer function after you can impulse response of the system. So after that you can get the response. So this is actually some finite position it is starting, and after that time will be increases, and you can get some response that will be to the 2 tends to infinity. Okay, now I will also marking here, this is the stable region, this is the stable region, the negative half of the S-plane, and this is the positive half of the S-plane, this is the unstable region. So pole location of the S-plane, which position pole will be placed in the right half or left half, that actually matter to stable system, unstable system, or marginal stable system. So marginal stable system, actually here some pole actually exist in the origin, so that time one pole, so that time you can say system will be marginal, one pole, but multiple pole will be exist, so that time you can say system will be unstable. Another, here some pole and here some pole, symmetric pole in imaginary position, this is actually minus 3j, and this is the positive 3j, and this is the minus 3j. So at that time symmetric pole exists, so that time also it is marginal stable condition. Okay, marginal case, that actually system will be some response at that time you can see said that this is the system will be starting from the 0, and after the magnitude will be same with respect to time. So this will be the marginal stable condition. This is the oscillating type of system. You can say this is the Ct and this is the T. So at that time your system response will be, this is actually nature. So oscillating type of signal, the magnitude will be fixed. This is the positive and this is the negative. This is the magnitude will be fixed, and it is oscillating type. It is not tends to 0 or not tends to infinity. Okay. Now condition for stability. Condition for stability, if transfer function we know Gs equals to Laplace transform output to the Laplace transform input at the all initial condition is to be 0. So ys by xs, so this is actually numerator and this is the denominator. We know this is actually numerator portion, we can calculate the 0, and denominator portion we can calculate the pole, and that pole vital role play because this is actually characteristic equation. So closed loop system, we know gs 1 plus gs hs, this is actually generalized transfer function. So that 1 plus gs hs equals to 0. So this is actually characteristic equation. So if the transfer function of the system you can calculate after the denominator portion equals to 0, that actually your characteristic equation. Okay. Now the system having characteristic equation, I already said this is the denominator term equals to 0. After that, some criteria for condition for stability. Number 1, all the coefficient of the above characteristic equations should have same sign. Means if the characteristic equation, this is the positive sign, so all should be positive sign. If negative one, so all should be negative one. Okay. Now second point is there should be alternative term, that is there should be no any missing term. Missing term means if s to the power n, after the s to the power n minus 1, s to the power n minus 2, in this way dot 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 s to the power 1, s to the power 0. Missing term means suppose your third order equation or fourth order equation s to the power 4, s to the power 3, s to the power 2, s to the power 1, s to the power 0. If any term will be missing, suppose this term will be missing, so at that time the condition for stability will be break down. So that time you can say that system will be stable, unstable. Means these two criteria is when it is satisfied, at that time you can say the system will be stable. But this is actually not a stable, this is actually necessity consideration for stability but not sufficient condition for stability. So thank you. Next class I will teach you the sufficient, when these two conditions not match the sufficient condition, this is the necessary condition not satisfied, so what will be the criteria and what will be the approaches to calculate the stability analysis. Okay, thank you.